Hello and good morning from here in Dallas, Texas, and good afternoon or evening to you all in Paris. My name is Alex Demetrius, and along with Renee Glover, we want to thank you for including our talk as part of the CloudStack Collaboration Conference. I apologize for not being with you there in person or even live and presenting virtually, but it is a holiday here in the US, so we opted to instead provide a recorded session. I can promise, however, that my wife is especially sad we did not travel to be with you all in Paris. Since we are not there with you all, that obviously means we are not able to take part in any Q&A, but perhaps, Yvette, if there are any questions from the group, you can forward those along to me, and we will do our best to get some answers back to you all soon. During today's talk, I'm going to discuss our journey with CloudStack and how we are using CloudStack and GitOps at scale within the enterprise. So who are we? Our organization is responsible for development and support of multiple application infrastructure platforms, frameworks, services, integration layers, and observability tools. One of these infrastructure platforms is our distributed, centrally managed Kubernetes platform, which runs on-premise. We have somewhere around 50 Kubernetes clusters made up of thousands of bare metal and virtual machine worker nodes. And our platform supports tens of thousands of microservice containers across multiple areas of the business. So we have some experience operating enterprise-level infrastructure platforms. And where we can, our team chooses to use open source technologies when implementing new solutions for the business. Now, enough about us. Let's jump into our journey with CloudStack. Now, I'm no Tolkien, but I will do my best to make this an interesting story nonetheless. So here's an overview of the story I'm going to tell today. I'm going to start with a short introduction of our problem statement, and then quickly jump into talking about our journey with CloudStack and our platform. I'm going to provide an overview of GitOps and talk about the architecture we have used to manage our CloudStack-based platform using GitOps. And finally, I will share some quick hits on the success we have had with our CloudStack-based platform so far. So how did we get here? Our team saw a need to solve a long-standing problem on how we do infrastructure provisioning within the enterprise. The previous model relied on an ordering-based system and a waterfall model, often resulting in delivery timeline of weeks or even months for virtual capacity. Over the years, there have been several homegrown and what are now considered legacy tools built to fit within this waterfall model. These tools often require numerous system integrations between them, which results in points of failure, further delaying our ability to deploy needed capacity. Because this ordering is done on an application-by-application basis, our capacity can often become siloed, resulting in areas of poorly utilized resources. And as you can imagine, attempting to forecast compute or storage needs for a brand new application is extremely difficult. So often orders include worst case or peak use estimates, and then maybe even 30% additional resources for unplanned overhead. And as application teams become frustrated with delays in receiving capacity, this can also lead to further over-ordering over time. However, we've made significant progress in modernizing much of our application landscape. With our recent journey to migrate applications to public cloud, our software development teams have grown accustomed to the ability to provision resources on demand, at scale, and use best practices for infrastructure as a service using models like infrastructure as code and technologies like Terraform and Packer. In addition to becoming more familiar with infrastructure as code deployments, our application teams are also more accustomed to deploying resources within a private or isolated networking model. And finally, most, if not all, of our software development teams within the business already use agile development practices. So our team set out to provide a platform that can enable this same agility for on-premise infrastructure provisioning. So why CloudStack? After reviewing and performing some proof of concepts with a few different cloud management platforms, we, of course, landed on CloudStack. Since this is a CloudStack conference, I don't need to go into detail on all the reasons why we chose CloudStack as our cloud management platform, but I will mention a few features that we were specifically drawn to. For instance, CloudStack Projects provides the tenancy model that we were looking for, as my team is deploying CloudStack as a centrally managed and centrally supported infrastructure as a service platform. And Projects allows application teams within the business to maintain their own dedicated tenant environments. This model also happens to align to our public cloud patterns. The CloudStack Terraform provider and APIs allow teams to continue using infrastructure as code, whether deploying on-prem, in public cloud, or in a hybrid model. Project quotas and the usage server is also an important feature for us for several reasons. Project quotas enable us to force application teams to properly optimize their resources, since we, the CloudStack administrators, control the keys to quota increases. The usage server in CloudStack also enables us to perform showback or chargeback to the various business units as needed. We can also charge differently through custom service offerings for non-standard compute, such as GPU-enabled hosts. We also have the ability to force optimization of capacity with over-provisioning. For instance, if we notice a certain zone or data center is less utilized than others, we can improve utilization simply by adjusting the over-provisioning factor, forcing more workloads onto fewer hosts. And last, we desire to manage this infrastructure as a service platform using a GitOps model, and I'll talk more about GitOps shortly. Now, every good story has some conflict, and we did face some issues when first deploying our CloudStack-based platform. And just to be clear, these may not necessarily be items we consider as issues with CloudStack itself, but gaps we needed to close as part of our specific solution and use of the product. So we felt it'd be good to discuss them here in case any of these items become areas the community also has an interest. I outlined a few specific items here, such as FreeIPA as a UAM solution, Metal as a Service or MaaS as a bare metal host provisioning solution, reusable Golden OS templates, and platform monitoring and observability solutions. The first gap we encountered was a need for a more seamless user access management solution to managing SSH keys and access to CloudStack VMs. We wanted to maintain the ability to use roles and permissions within projects in CloudStack. However, running VMs cannot capture changes made to these roles or changes in SSH keys without stopping or rebooting the VM. So we chose to deploy FreeIPA as our UAM solution for CloudStack, as it is also an open source product. To make this possible, we include the IPA client within our VM templates. We also wrote some extension code for CloudStack, which watches for specific events and sends those events to FreeIPA. So here's what that looks like. A project role in CloudStack is created as a group in FreeIPA, and users within the project role are added to that FreeIPA group. Now, for example, if I have a project role which I want to grant the ability to SSH and perform sudo commands on the VMs within the project, I create these allow rules with SSH all and sudo root all. If I add to or remove users from that role, that information will be updated in FreeIPA in a matter of seconds, and the user has access and sudo permissions to all of the VMs within the project without having to restart any of the VMs. If I instead want to use something like instance groups to further restrict access for a set of VMs, for example, only my database VMs, I can do that as well. Here I have an instance group I named databases, and I created a new role for my DBAs, which allows them to only SSH into VMs that are part of the databases instance group. And then they can become the MySQL user and perform any command as that user. The next item our team looked to address was around the bare metal host provisioning. And for that, we landed on Metal as a Service or MaaS. Since our CloudStack-based platform is likely to become the primary infrastructure as a service platform within the enterprise, we needed a way to automate the provisioning and configuration of our KVM hosts, especially with the expectation that the coming years may see our platform grow to hundreds, if not thousands, of bare metal servers. To solve this, we deployed Metal as a Service or MaaS. Once hardware is available on the network within the data center, MaaS takes over and handles PXE booting of the host and installation and configuration of the operating system, networking, storage, and management console devices like iDRACs or ILOs. As a part of this automation, MaaS installs the CloudStack agent as a systemd service on the KVM host and uses the CloudStack APIs to register the host and make it ready for scheduling application VMs. With MaaS and CloudStack, we have created automation that allows us to bring hosts into maintenance mode and perform operations like OS patching or run any number of custom scripts across all KVM hosts managed by MaaS. To make this possible, our team was required to make updates to both the MaaS and Redfish Terraform providers to support the ability to deploy an operating system onto bare metal. And you'll see a bit more detail on this later, but we also created a Helm chart and Docker image for MaaS to allow it to run as containers in Kubernetes. Next, to simplify our offerings of operating system flavors, as well as ensure compliance to enterprise standards, our team began producing golden images or templates for a number of operating systems like Rocky Linux and Ubuntu, and we also produce similar templates for databases like MySQL, Cassandra, and MongoDB. One of the primary drivers for providing a standard set of templates is to ensure compliance. So we include several required scanning tools within the images. However, we also use this as a mechanism to drive software currency. We do not keep older templates around for months or years. Instead, we are consistently providing a refreshed set of templates as a mechanism to encourage application teams using our platform to remain on the latest and most secure operating system versions. Within these templates, we are also baking in observability solutions so that application teams are not required to install their own metrics or log collection agents. We again use this as a mechanism to simplify and standardize the set of tools that we deploy across the enterprise. Within these templates, we currently install Prometheus Node Exporter, as well as FluentBit to capture both metrics and logs. We also configure the VMs to ship this data to our centrally managed Grafana instance. This provides a great experience to our tenants, since from the moment their VM is up and running, they are able to see their data in Grafana with no manual effort on their part. Last but certainly not least, we take monitoring our platform serious and are almost obsessive about ensuring we know everything happening on our platform before any of our tenants do. Just like writing documentation, we look at each release as an opportunity to review our monitoring and alerting coverage. I recalled some discussions from previous CloudStack conferences, and I know monitoring is frequently a hot topic item, so I wanted to share what we have done so far. Through MaaS, we deploy Prometheus Node Exporters and FluentBit agents on every KVM host, capturing compute and storage metrics and even systemd service metrics, so we can ensure that several systemd services like the CloudStack agents are running. Within our control plane Kubernetes cluster, we have deployed various other exporters, such as Black Box Exporter, which we use to perform pings against our KVM hosts, check API responses from several services like our CloudStack UI, and even check DNS lookup and resolution times. We use a MySQL exporter to capture crucial database performance metrics, and a SQL exporter, which actually performs SQL queries and returns the results as time series metrics, so they can be visualized in line with other metrics. Since MaaS uses a Postgres database, we have deployed a Postgres exporter capturing similar database performance metrics for MaaS. We also recently deployed an IPMI exporter, which actually captures critical host information typically only visible from the iDRAC or ILO management consoles. With the IPMI exporter, we can capture power status and power consumption metrics, server fan speeds, motherboard temperatures, and hundreds of other various sensor metrics. We have also begun performing some initial POC work on storage array exporters, and all of these metrics we visualize through a central Grafana instance, allowing us to visualize metrics and log data from multiple sources within a single pane of glass to fully monitor our systems. We've also created a robust set of alerts in Grafana to ensure we are immediately notified of any issues with our platform, and these alerts are sent to our Microsoft Teams channels as well as our paging systems. Did I mention we like open source technologies? But who doesn't love data visualization? So here's a couple examples. And while I would have liked to provide a live demo of these dashboards in action, it proved very difficult to obscure all of the information we need to keep private. So I'm opting for some screenshots instead. The first dashboard here is showing IPMI exporter data for one of our KVM hosts. You can see the metrics for things like fan speeds, power state and consumption, system board temperatures, and all the metrics you would previously need management console access to view. And these IPMI exporter metrics are even more useful when within the same dashboard, you can see compute and storage metrics from Node Exporter for the same host. And if I were to continue scrolling further down in this dashboard, you can see system log information for the same host as well. All of these metrics and logs are visualized in a single place, and both our development and operations teams have access to view this information. Via our MySQL exporter, we have our MySQL database metrics. This has been especially useful these past couple of weeks as we have been working to enable high availability for our KVM hosts. And with this dashboard, we've been able to keep an eye on the performance of our MySQL database. Now, I mentioned we also provide a similar experience for our tenants. Here's an example dashboard using Node Exporter metrics, which provides visualization of all of the VMs in one of our tenants' projects. So at the top there, you can see an overview of metrics for all of their CloudStack VMs. And we can also filter to see specific metrics for a single VM, like what's represented underneath. Now, this is just a snapshot of a few visualizations, but if you've used Node Explorer before, you know it's extremely powerful and can capture nearly every metric imaginable from a system. And it's not just dashboards. Our tenants are also able to configure their own alerts within Grafana in a self-service manner, leveraging all of the same capabilities for observability that we use for monitoring the platform itself. I hope this provides interesting discussion material and maybe sparks some ideas on open source solutions for other CloudStack users. Now that you've heard about our journey with CloudStack, it's time for me to move on to our next chapter, GitOps. Some of you may already be familiar with the concept of GitOps, but just in case, I'm going to provide a brief overview. I included this link to the Weaveworks blog post on the 6 ideas shaping GitOps today, as one of the ideas is specifically around self-service developer platforms, which is precisely what our team aims to provide for the enterprise. And I would highly suggest you check out many of the other blog posts on GitOps as well. So what is GitOps? Simply put, GitOps is a way to manage our software and infrastructure in a manner that relies on Git as the single source of truth. In essence, the actions of pull requests and merging a branch of code results in immediate reconciliation of these changes to our platform. This process allows pull requests to act as decision or approval gates. But to reiterate, merging a branch of code results in that application being immediately updated to the new target state in the target environment. GitOps does have a set of principles defined by the GitOps community, and I've provided a link to the open gitops.dev site below where you can find some more information. Starting with the first principle, a system managed by GitOps must have its desired state expressed declaratively. Desired state is stored in a way that enforces immutability, versioning, and retains a complete version history, like a Git repository. Software agents automatically pull the desired state declarations from the source, and software agents continuously observe actual system state and attempt to apply or reconcile the desired state. Now, I want to be clear that with GitOps, this continuous reconciliation mechanism is a pull, not a push. So having a Jenkins pipeline or some other job that automatically triggers and then pushes or deploys something, maybe CI/CD, but it's not GitOps. Rather, you need a software agent like Argo CD or Flux2, which performs this pull and reconciliation, which I'll talk about more in just a moment. So why use GitOps? First, GitOps has built-in approval chain and audit trails. The workflow to deploy is as simple as a pull request and merges, and those pull requests can hook into both automated and human approvers. Because state is constantly being reconciled from our source of truth, our Git repository, there is built-in drift detection. Any change made directly to a resource outside of Git will be reverted back during reconciliation, enhancing the security of our environments. GitOps allows us to scale our infrastructure platforms and applications without duplication, as you can create and manage configuration which can be reused at a global, location-specific, environment-specific, and all the way down to an application-specific scope. Therefore, GitOps is a great fit for Kubernetes because everything is already declarative, since Kubernetes resources define the desired state, and you can use controllers to reconcile state changes defined by your resources. And just like any Kubernetes native solution, Flux works the same way. So what is Flux2 and how do we achieve GitOps with Flux? We deployed Flux on one of our Kubernetes clusters, and it is configured with our Git repositories as its source. Essentially, Flux watches for state change on a specific branch or branches, like our main branch, and using various Flux controllers like source, helm, and customize, applies the change to the necessary resources. It may be easy to assume what many of these controllers are responsible for by their name, but one that may be new is customize. And yes, that's customize with a K. Customize allows you to generate Kubernetes resources without duplicating the definition of shared configuration across every application instance. It achieves this via a system of bases and overlays. So if you think of a base as something you may want to be applied across every Kubernetes cluster, for example, you deploy Prometheus in every cluster, you would only define this once within the base. But if you happen to have an application that you only choose to deploy into a UAT environment, for example, maybe something for performance testing, you can use an overlay that defines this performance testing application for just that specific environment, set of clusters, location, etc. Kustomize was designed specifically for GitOps use cases, and it does much of the heavy lifting for Flux 2-based solutions. And last, Flux 2 has many other features, such as the ability to reject deployments and perform automated rollbacks, send alerts or notifications for deployments, provide automatic encryption and decryption via SOPs, and much more. So how does CloudStack fit into this GitOps model? I put together some high-level architecture slides to represent what this looks like. Here's sort of the 10,000-foot view of our zone topology. For obvious reasons, I'm not showing actual geographic locations of our CloudStack zones, but this provides an example of how we've deployed these technologies. We've deployed 2 zones in what we call our central control planes, indicated by the red-colored buildings, and every other zone contains a site control plane. And our data plane, comprised of our KVM hosts, runs in each of these sites. If I zoom in a bit, we have one of our central control plane clusters. This is a Kubernetes cluster where our Kubernetes master nodes reside. Within this site, we have the CloudStack management servers deployed as containers. We have our FreeIPA containers, various Prometheus exporters, as well as our MaaS containers such as RACD, RegionD, and the MaaS Postgres database. On our 3 central control plane nodes, we do not run any application workload VMs. If we look at our site control plane and data plane architecture, we can see that each site has 3 KVM hosts, which act as our site control plane. And here we actually do run application workload VMs, as well as RACD for MaaS. And as I previously mentioned, each KVM host runs the CloudStack agent as a systemd service. Now, I need to note that at this point in time, our data plane is not yet managed by Kubernetes, but that is our target state, and we are working to make this functional very soon. Finally, let's put this all together and see what it looks like to manage CloudStack using GitOps. Let's take an example use case of wanting to increase the number of CloudStack management servers from 3 to 4. Since our management servers are running as a replica set in Kubernetes, we could just go into the Kubernetes dashboard or use kubectl to scale up the number of replicas. But in doing so, we risk introducing inconsistencies. For example, what if we forget to apply the same change in our secondary control plane cluster, or introduce discrepancies across our different environments? Also, if we don't remember to go back and update our pod configuration in Git, the next time we perform a deployment, our replica set will again only have 3 replicas. This deviation is called drift. And while this one small example may seem harmless enough, drift can quickly result in a lack of consistency across our environments, often leading to unnecessary operational overhead, especially when it comes to platforms operating at enterprise scale. So knowing we are going to only make this change in Git, we make our pull request, it is reviewed, approved, and merged. Flux recognizes this new declared state, and through the Kustomize and Helm controllers, applies the state change to our CloudStack resources in Kubernetes. The same process is followed for all of our GitOps managed resources, whether it be CloudStack, MaaS, FreeIPA, Prometheus, and much more. So let's see this in action. Again, I apologize for not including this as a live demo, but hopefully with a few slides, you'll have an understanding of GitOps in action. What I'm going to do is, what I'm going to use to demo this are 3 things: our Git repository web interface, kubectl, which is a Kubernetes command line interface, and last, our Flux command line interface. First, here's the current state of our CloudStack management containers, where we can see from the kubectl command line that we have 3 replicas currently running, and they've all been running for the last 12 days. Now, here we are in our Git repository, and the team has made a commit and pull request to update the number of replicas from 3 to 4. And if you remember, Kustomize allows us to make this configuration change in many different ways. Here, since we are doing this just for demo purposes, you can see we're only applying this change to a specific cluster, which is one of our test clusters. But we could absolutely make this same change to the base configuration, which would apply this configuration everywhere if we wished. And we would only have to update 1 configuration, regardless if we are updating 2, 12, or 100 clusters. Next in our process, the pull request has been approved by others on the team, and we are ready to merge the branch back into main, which is the source branch that Flux is watching. I should add that human approvers are not the only ones that have approved this PR. As part of our automation, each pull request and any subsequent commit to an open pull request triggers a Jenkins pipeline to perform several code validation tests prior to us merging anything back into main. And this bot is also an approver within our workflow. Now, if I return back to my terminal, I can use the Flux command line at the top to check the status of our Helm release. In the top terminal, I'm checking the status of Flux reconciliation, and you can see here that after a few moments, we go from reconciliation in progress to a successful reconciliation. In the bottom terminal, I can use the kubectl command line to check the status of the CloudStack management containers. Immediately after reconciliation completes, we can see our fourth container being created, and after a few moments, we have all 4 containers running. And thanks to Flux, this was all accomplished through merging of a branch of code. Now, some organizations, like ours, have strict controls on who can trigger a production code change. So how does this GitOps flow work within a DevOps team while still maintaining the concept of separation of duties, which prevent a developer from pushing code directly into production? Here's how we've solved this problem. Our platform development team makes code commits, creates pull requests, and reviews and approves code, just like I mentioned on the previous slides. Once this change is scheduled to be released into production, our operations team members suspend the Flux reconciler, which stops Flux from watching the changes in our Git repository. During our scheduled maintenance window, the pull request or branch is merged, and our operations team resumes Flux reconciliation, which begins the deployment process. The changes are validated, and assuming everything goes off without a hitch, our work is done. As I mentioned, Flux has the capability to automatically back out or revert changes in case reconciliation is not successful. And in the event that all of our test cases pass, but we still encounter an issue with the deployment, the development team stages a backout pull request, which can be quickly merged and to update our source back to the original state prior to the change if needed. Now, sadly, I've reached our final chapter of our story. But happily, I get to share some of the successes we have had since using CloudStack and launching this new platform. It's been just around 6 months since our project was officially approved to move forward. And since then, we have deployed KVM hosts in multiple data centers via MaaS and enabled them within our CloudStack zones. We have begun introducing early adopters to the platform and have already seen adoption grow to dozens of new VPCs, guest networks, and projects, and recently achieved a milestone of 1,000 VMs running in CloudStack on KVM. Now that we have a solution allowing for rapid provisioning and dynamic scaling of virtual resources, application teams are no longer having to waste resources by keeping VMs in reserve for peak periods. Our initial use of the platform has seen a 50% reduction in allocated CPU and memory so far, as applications have moved from our legacy model into CloudStack. Now, I want to caveat that the majority of these reductions are coming from idle or reserved capacity, which made these easy targets for reduction. So we don't expect this to be a trend long-term, but it is an accomplishment nonetheless. Our team has recently also submitted a pull request to the community for the fiber channel multipath solution for KVM, where we hope to see a vendor-agnostic solution to using fiber channel storage for KVM-hosted workloads maintained by the community long-term. Last, we have successfully implemented an architecture that allows for GitOps management of this platform. Thank you all for allowing us to share our journey with CloudStack, and we look forward to collaborating with you all and maybe even see you at next year's CloudStack Collaboration Conference.